Vision language models can generate original text and images, but can a vision language model generate 3D designs for assembly by an industrial robot? We propose generative design for robot assembly, or GDFRA, a new type of problem where the goal is to generate an assembly design. There are two inputs, an image of available components and a single word or phrase describing the desired shape. The output must resemble the requested object and be reliably constructible by a robot. To address one class of GDFRA, we present Blox-Net, a three-phase system combining generative AI, physics simulation, and a robot arm with a suction cup to design and execute assemblies using 3D printed blocks. Blox-Net takes as input a top-down image of 3D printed cuboids and cylinders, and a word or phrase describing the desired shape, like sheep. In Phase 1, Blox-Net uses a vision language model to generate assembly designs from a prompt and available components. The process starts with a three-step prompt. First, the VLM outlines the object's parts. Second, it matches these parts to specific blocks from a provided list. Third, it considers the assembly order and spatial relationships between parts. Finally, with planning complete, the VLM outputs the shape, color, dimensions, and coordinates for each block. This design is built in a PyBullet simulator, which gives visual feedback by rendering images of the assembly and stability feedback by identifying unstable blocks and the direction in which they fall. Based on this information, the VLM updates its design, improving stability and structure characteristics. 10 designs are run in parallel. Then, the VLM performs head-to-head comparisons, choosing between candidate designs until converging on a final design. Additional generations, including animals, structures, and letters, are shown here. Phase 2 involves a simulation-based perturbation redesign, where the VLM-chosen design undergoes iterative refinement in a physics simulator. Block placements are simulated with small placement errors and checked for collisions and instability. Through repeated simulations and adjustments, the design evolves to better withstand real-world variances in assembly conditions. In Phase 3, a robot arm with a stereo camera pair and suction gripper constructs the optimized design. We find that perturbation redesign improves the full assembly completion rate from 28% without perturbation redesign to 96% when perturbation redesign is applied. Surprisingly, Blox-Net manages to correctly place 99.7% of blocks successfully. Here we see Blox-Net in action, autonomously assembling generated designs across a wide variety of objects. Experiment results suggest that Blox-Net can bridge the gap between abstract design concepts and robot executable assemblies. Remarkably, 5 Blox-Net assembly designs, each consisting of 3 to 10 blocks, were successfully assembled 10 consecutive times by the robot without human intervention. For more details, please refer to our paper or visit our website.